get going this morning and jump right in. If you have a question, I am looking at the sidebar. So if anybody has a question and they want to raise their hand, they can, and I will see it on my end. And if you have questions in the audience, I think I heard Crystal say that you had microphones, so you can just, I can hear, hey, I have a question, and then we'll go from there. Okay, so let's get going. Oh, this is my, down at the bottom here is my email, Twitter, Instagram. If you have questions, please email them to me. And I'd be happy to try answering them. I will have a network up and going, a subscription network up and going next week. So you'll have an opportunity if you want to have more interaction, ask questions on a regular basis, follow our information, etc. You'll have that opportunity through the network. And that is jillclapperton.com. Okay, well, I'm going to do two parts today. The first part, we're going to talk about soil organic matter for the most part, how we build it, how we, and how plants contribute to it, what it is. We're going to go sort of through the who, what, when, where, and why. I'm not going to talk about all the critters that live in the soil because I'm going to make a presumption here, and I could be wrong. I admit it. You all could have a pretty good idea of what they are and what they do. And we'll just have to see what happens as we go. If you don't, please let me know, and we can adjust on the fly. That's the beauty of this. Okay, let's see if I can forward my next slide. Huh, interesting. There we go. All right. We're going to talk about soil health. As you can see, we've got, I'm going to use the mouse. We've got the biology at the top, physical, chemical, all create soil health. The biology is at the top because it really unites and integrates the chemical and the physical properties of the soil. And then soil health is related to soil productivity. And we're not just talking about, yields, bushels. We're really talking about food quality. How nutrient dense is our food? Because we would like our food to be seriously nutrient dense. We're talking about environmental quality. We know that farmers can have a real role in mitigating climate change. Let's use that role. Let's take advantage of that role. And ultimately, if we can do all of this, we have a direct link of soil health and biological activity of the soil to our own health and the health of our animals. And this is what we're going to focus on. And you'll see how this kind of all integrates as we go on. So, in a healthy soil, your plants will be thriving. And, I'm convinced as I farm more around the world that soils actually have a holding capacity. It's meaning that, our plants genetically may have more yield, but I'm not sure that our soils always do. At least they don't always in the state that we might have them. Some people have actually changed their soils quite dramatically. And like David Brandt in Ohio would be one of them, where he's changed from a mostly clay to a clay loam. So, we know they can change. It's not overnight. I mean, that took him more than 20 years. So, but we know we can do it. We can do that too. But plants are thriving. We have good soil structure, regardless of what soil type we have. We have the best soil structure we can have for that soil. So if it's sandy, we still have a few aggregates. We don't have everything rushing right through. We have some organic matter. We have a large number of functioning soil surfaces. One thing that we are going to definitely do is limit our erosion. We don't want soils running off. I know in southwestern Kansas, where I have a large ranch there, we have serious ditches in some of our crop fields, which spill well into some of our grasslands. And, part of that's the problem with that is not that the terraces and not bad terraces or broken terraces. Part of it's just that the water doesn't go in the ground, and that's soil structure. And so we need to improve that. Um, but on the other hand, I have on my innate soils in southwestern Kansas are highly prone to erosion. You just have to go there and look at the landscape and know that there has been some serious erosion. Um, Good soil. So we have increased nutrient cycling. We should have increased CECs. That's going to come with organic matter. We should have increased water holding. We should have better filtering. We should have more recycling of nutrients. And if we get everything right, the microbes actually will break down all the toxins, and everything, and our water quality will be better as well. We'll have a diversity of soil organisms because we're not just feeding them one kind of organic matter. We're feeding them a whole smorgasbord of good things. And we will have healthy, nutrient dense plants. Now that we've created that habitat, and the first thing that we're going to do to create that habitat is we are going to minimize the amount of tillage that we do. It really is the only way, if we're going to do this. So let's minimize the amount of tillage and start building the habitat. Because you have to think about it, all the organisms in our soils have put a lot of energy into building infrastructure in the soil. And if we destroy it all the time, like plow through it and whatnot, well, they're only going to have so much energy before they're going to give up and move somewhere else, or just not bother anymore and rest in the soil, which most of them are capable of doing, is resting for a very, very long time and wait until things get better for them. So what makes the soil gain? When we talk about a healthy soil habitat, it's about good soil structure. It's about having those continuous soil pore spaces. You'll know because you'll have really good infiltration. So one measurement of soil structure, it's an indirect measurement, but it's perfectly valid measurement, would be to actually look at infiltration. You can do it in the field very easily, and just check it out. You'd be surprised. But good infiltration means that we're testing water moving through, water holding capacity. You'll have a good idea of soil structure. You'll have predator-prey relationships, because if you have good soil structure, you'll have room between the pores for water to move. And most of our really good predators, the ones that feed on the bacteria and the fungi, actually move through the soil on water films around the pores. And so you can think about it, it's like a maze, and they're zooming around on these water films around the pores, looking for bacteria and fungi to eat, looking for bits of organic matter, looking for other things. And we need the predator-prey relationships, because it's our predators that really concentrate the nutrients that are recycled. So that's a really important thing. No, there we are. So another way that you can do this very easily is just take a soil core. You'll see that this is a water bottle, right? It's just a drinking bottle. And all we did was cut off the cone part of the bottle, turn it in, and then reverse it and stick it into the bottle itself. So we created a capture point, and then we just poured water through the cores. And you can see that if you look at the one on your left, you'll see that one, the soil has collapsed. We've got a lot, no, we haven't got, and because of that, we don't have a lot of infiltration, right? Because the soil is actually collapsed, and you can see that we've got a lot of water in here. It's just sitting there, not infiltrating. But over here, we've got water infiltrating, and look at how clean it is at the bottom. This is another farming contribution to water quality and environmental quality. So increasing the soil organic matter is going to regenerate and sustain soil health services and benefits. It's going to improve all these things, and we're going to talk a bit about that as we go through. This is a close-up look at some of what we'd call your recalcitrant organic matter, which means that the stuff that really doesn't break down and that something is going to stay in the soil, break down a little bit, maybe even from the sun, maybe just from weathering. And eventually it's just going to be there as a sponge to hold water and to attract nutrients. And ultimately, that's where we want to get to with our decomposition. So this is actually humus. So what do we have? We have stable organic matter and we have effective organic matter. Effective organic matter is just that. It's where the organic matter is actually binding a lot of our elements, holding our water, that sponge. Think of you, it really needs to think, you really need, the thing to think about is the soil like a sponge, and it's the organic matter that creates the sponge. And the sponge is holding all the nutrients, and it's a habitat for where all the interactions happen. And the roots are going into the sponge. And so they have the advantage of sucking things out of the sponge as they go through. And ideally, we want our roots to go into a sponge, because not only is it holding water, but it's also holding nutrients. So even in the driest of times, they still have access to a few things, which is important. Now, this is a gray wooded soil from northern Canada. And I use this soil not because it's a great soil, because it is really great for growing trees, but because it's a gray soil, you can see where the carbon has oxidized and the roots have gone down very clearly, even the fine roots. You can see where they were before in this soil. Over here is an earthworm channel. Again, you can see the oxidized carbon of how it moved through. See how we're building soils, because even though the root is no longer there, it still left its carbon footprint. It still left its shadow, its carbon shadow. So we can still see it. And that carbon is in there, and it's effective carbon. It's going to hold water. It's going to hold nutrients. And any root that moves down an old earthworm channel or moves down an old root channel is going to have the advantage of that. This is from the Nature Conservancy, and you can see that, you know, we are losing organic matter. Now, the work that was done over 100 years ago in the US and Canada shows very clearly that when we started to do the plowing, every year we plowed, we lost 32% of our organic matter. And then once we got into better crop rotations, et cetera, we started to only lose 16% a year. And now we're probably down to losing about 3% a year, depending on how we're doing things. And if we continue with building root canopies and we can continue on reduced tillage, we can actually start to rebuild that soil organic matter to all of our benefits. So let's talk about let's talk about the soil food web. I think, you know, and I'm doing these Zoom meetings, I think I'm still putting on my presentation voice, and there could be, all of you could be in this room with me. It'd be a little crowded. We wouldn't be able to social distance, but I think I'm still using my projection voice. Anyways, soil food webs. Soil food webs are mainly based on 3 primary forms of carbon. Root exudates are the primary one. So oftentimes when we are talking about carbon, we're thinking about residues on the surface. But actually, the most active form of carbon is the carbon that is being exuded from the roots all the time. And you know, this is something that we don't think about because we can't see it. So always like out of sight, out of mind. But really, this is one of your most important sources of carbon, and it's active, super duper active carbon. It's like the liquid straw carbon going straight into that area around the roots, feeding all those microorganisms. And the rhizosphere, that area around the roots, is the most biologically active place in your entire soil. The litter and the residues, of course, are a good source, but they have to be buried. And we need earthworms, and we need our microarthropods and things like that to actually start burying those things. And the soil organic matter itself. This is, again, old root bits, dead organisms, you know, the mucus and the waste products of bacteria and fungi. All of those contribute to the soil organic matter as well. And rotation has a big influence. And most of it is the fact that higher carbon residues tend to last longer. So roots that have a lot more carbon in them tend to last longer in the soil. Because what happens is the bacteria and the fungi use up all the nitrogen when they have a lot of carbon. And so it slows everything down. Whereas when we have a lot of roots in that have a lot of nitrogen in them, then the organisms will preferentially break those down, take more nitrogen, take more carbon, and make more organisms, which is not always a good thing, because bacteria and fungi can outcompete a plant at any time for nutrients. And we focus when I hear people say feed their microbes, they're thinking they need sugars. They actually don't. And what really controls populations in and around the ground is nitrogen, and all the other minerals. They need access to iron, they need manganese, they need a lot of the things that we need and everybody else needs. And they're just a whole lot better at getting it than the plant is. So as long as we give them the carbon chains, they'll go around scavenging for the other things so that they can use the carbon. So what we want to do is find that balance where we have enough nitrogen and enough minerals that we keep everybody happy. So one of the things is that when we grow pasture or we grow a forage cover crop, we usually don't have just one thing. We have the grass because we need grass because grass makes milk, grass makes beef, grass makes lamb, all of those things. But we also need to have more of a balanced diet. So we give them more of a salad bar. And when we do that, we actually are creating a higher quality organic matter. And that tends to stay in the ground. And we're creating more roots. So the more roots we have, the more we have carbon in the soil, the more organic matter we create. And not just any organic matter, we create a higher quality organic matter. But let's look at the fact organic matter as the sponge, this idea of it being a sponge. So I want this to be a little interactive. So I'm going to ask the audience now, and you at home can also answer. Just take your mics off mute. Is what are these dry patches that you see? This is in the Palouse. This is a big hill. This is CRP in the foreground, and this is a wheat crop in the background. So what are we seeing here? What is this? What are these dry areas? And I should warn you, I will stand here for a very long time until someone answers.
Looks like soil type. Looks like soil type.
Yep, it's soil type is part of it, absolutely. What about the location? What are you noticing? There's a pattern there.
Hills.
Yeah, knolls, hills, eroded knolls. So as they've been tilled over time, and even though this is no-till, you can see that the tops of these hills are just drying out. And the crop, we just are not growing a crop on them at all. So we asked ourselves this, well, okay, I mean, clearly this is going to take a bit of time. Do we, just pile up a bunch of hay on them and mulch them? Or do we put like organic matter in the ground, like just sort of take it a next step? And so what we did is we pelleted a bunch of compost, and then we seeded the same field with pelleted compost. And it had an 80%, 87% water holding capacity. And it was solid organic matter, composted organic matter. And now you can see that it's gone. That's just the effect of water holding capacity. It's powerful. Now, I talked a little bit earlier about how important it is that the soil organic matter there's a quality to it. And that's that carbon to nitrogen ratio. I'm not going to talk about the phosphorus ratio, the sulfur ratio, the macro and micronutrients, because all of those are actually really important in here. But 30:1 is what's standard in all your textbooks. They'll talk about 20:31 as being active carbon, which is required in the soil in order to break down and recycle nutrients and build your organic matter. But what we have subsequently found with a number of regenerative farmers is that 50 to 1 is probably more like it. Because when we start to get really into the 30 to 1 point, we start to lose a residue cover. We may have a lot of good soil organic matter, but now we start to lose residue cover. And the residue cover is really important to insulate the soil. A lot of people don't really understand the value of insulating your soil with the residues. Um, it's about maintaining nutrient uptake no matter how hot the temperature gets. So in Washington, for example, we have been experiencing really hot summers. So we grow a lot of cool season cereals and pulse grains. And what happened was June 1 turned into 100 degrees and it stayed 100 degrees for pretty much the entire month. And warm season plants don't like that. I had dead plants with moisture in the ground. Who would have thought it? And but what was really interesting to watch was where I had, where the combine hadn't worked very well, but I still had plants and I had this big pile of chaff from the combine. All my plants were still alive. So these little patches, which was really obvious that I needed to work on the combine. But I had all these patches of plants that were really alive, and I started to really research the effects of mulching. I've seen that on trees as well. And what happens is that if we can insulate the soil and we can keep that soil temperature at that 70 to 80 degree mark, our plants will transpire, will maintain the transpiration stream. And when they can maintain the transpiration stream, it really doesn't matter how hot it gets outside, they'll sweat and they can keep maintaining uptake of nutrients no matter what. So just bear that in mind, that you need the soil organic matter because we need the sponge and we need that exchange of nutrients, but we need the residues on top too to insulate against those super high temperatures. So we can actually maintain plant growth no matter what in these hot temperatures. And the other thing is that if we maintain the transpiration stream, we can keep the calcium and the boron and whatnot going up. If we think about corn stalks or corn crops, we can actually keep that going up into the plant, which means that we're going to fill those cobs. We're going to actually take a crop. And that would be the same with soybeans. And it's true for wheat and many other crops. If we can maintain the transpiration stream, we can maintain the fruits and the grains. And that would be, so in tree fruits, it's exactly the same. We will maintain the transpiration stream if we can keep the soil temperature low enough that the roots stay cool. And that also means that the soil microbiome keeps functioning, because they don't function very well above 80 degrees either. We really want to reduce leakage from our system, because if we're going to call ourselves healthy soils, then our healthy soils don't leak. They don't have like a leaky gut syndrome. We're going to hold on to the nitrogen, we're going to hold on to our mineral nutrients, and we are not going to be leaching them into the environment. This is about that whole idea of nitrogen, how we can grow our own to a certain extent. So what we have here is we have a field of wheat that's growing on a previous experiment. You can see the alleyways between the experiment. And in here, you can see all the plots where they're really green. This is where we grew alfalfa for 1, 2, or 3 years. It didn't seem to matter how many years we grew it for. But 20 years later, you were still able to see all the places where it was. So the point is that every different root you put in the ground, it leaves its mark. And the woodier the roots, the more root biomass we can put in the ground, the more we build the sponge and the more we build the quality of the organic matter in the sponge. And it's always going to be released, and we're always going to have a certain amount of nitrogen available from that organic matter. And not just nitrogen, but phosphorus, sulfur, anything that the plant took up before. And I should go back to that. Alfalfa actually takes up a lot of zinc, takes up a lot of phosphorus, calcium, iron, manganese because of the nodules. And so you are also, getting in an organic form a whole lot of micronutrients, which is really important for plant growth and subsequent plant growth. So I couldn't not include some of these beautiful electron micrographs of soil mites. This guy is really cool, quite flat. You can see all the little feathers, we call them feathers, on the back, and we are going to go back. You can see all the feathers on this guy. What's really interesting about these soil mites is they don't have any eyes. I mean, this is the head here, and these are the antennae. Actually, they're not, they're feathers again, but this is the antennae here. You can see that they can move through the soil, they're moving into pores, but we know that every one of these organisms creates their own vibration, and they recognize each other through vibration. The beauty of nanotechnology. The technologies we have these days are just incredibly powerful for everything. And these guys are what's really important. They'll eat holes in the organic matter that allow the fungi and the bacteria to start breaking them down even more. They're going to eat each other. They make tiny little holes in the soil, but mostly it is their manure that starts to create soil structure. So once again, that idea that the biology unites the chemical and the physical structures of the soil and affects soil health. We need to find a balance between below ground and above ground productivity. And, we need to ask our breeders to think more about roots, and not just be thinking about the above ground. But this is the beauty of mixing plants. We can have this little guy really happy, and we can have this girl happy. And it's just about, we need to think about it just a little bit more. So if we look at this, we have in the background, you can see what the normal habitat would be. It's fairly dry right now. This is not irrigated, this is dry land, but you can see the lushness of here. Grass, broadleaves, they're getting moisture. This is a 3 pounds a day weight gain on these cattle. So we're looking for things like this. We want some flowers out there for pollinators. The last thing we want to be spraying, if we really don't have to, is insecticides. So pollinators in our cover mixes, even around the fields, are really, really important for maintaining our plant health. But these deep-rooted sunflowers, deep-rooted and Phacelia with all its fine roots holding the soil together. If you have a sandy soil, Phacelia is incredibly important for holding sands together. And ultimately, where does the carbon come from? It comes from the sun. It comes from photosynthesis. It's amazing. Plants in a day can actually assimilate enough carbon calories to power a 100-watt light bulb. I mean, they're phenomenal. If we could only harness that energy a little bit more. Photosynthesis, it's not just about carbon that moves the plant. Yeah, carbon it is. All these things have carbon skeletons. Amino acids, organic acids, lipids, carbohydrates, nucleic acids, they all have carbon skeletons, including all those fancy things like phytoalexins and all the secondary plant metabolites that fight diseases and fight pests off. They all are made of carbon skeletons, but they're not carbohydrates. They're not sugars. They're more complex. And that's the important thing, is that when we're thinking about rhodexinase, we need to think about how complex they are, because the organisms that are feeding off them want amino acids. They want lipids. They're looking for other complex minerals. Sunflowers on 300 millimeters of water, that's about 8 inches. But that's what happens when you can have good organic matter and you start to really have that soil sponge. And you notice how dense those plants are. That soil is completely shaded from the sun. So we are maintaining transpiration, which allows the plants to continually take up moisture and still, at the same time, you know, they are growing in hot conditions with little moisture. So photosynthesis, once again, now I go back, sunflowers are a warm season crop. We don't have a lot of broadleaves that we can grow in North America that are what we would consider to be warm season. But sunflowers are one of them. Cowpeas are another one of them. There are some legumes that are warm season. Warm season plants are very different from cool season plants. They have a more efficient photosynthesis, but they also shuttle a lot more carbon compounds on a regular basis from the leaves to the roots. Warm, cool season plants tend to hoard their carbon a little bit more, and they only shuttle carbon at certain times of the day. So, sort of like where you could graze carbon on a warm season crop, you would starve for a little bit and then get a flood with warm season crops. And you can see that on average, your warm season is going to make a whole lot more carbon because they're just going to take up more of it just because of their metabolism. So if we can have a balance of warm season and cool season plants in a mix or in the crop field, it's perfect. Oh, look at that. Huh. So what we did here, this is Claresholm, Alberta, and you can see here that we've actually got three things growing in this field. We've got sunflowers, as you can see. This is the cash crop. This is what was considered to be the cash crop. These are faba beans growing between the rows. And then down there, just at the very bottom, you can just see the crimson clover. The idea was to feed nitrogen at the time that the plants were growing to the sunflowers and cover up the soil so that we didn't have to deal with bugs. And this also was a pollinator in here. So the idea is that we didn't have diseases, we'd have nitrogen, and we'd have pollinators for the sunflowers and to keep some of the aphids and things like that in check. It actually worked brilliantly. But it was a twofer because after the sunflowers were harvested, the faba beans matured, and we took a faba bean crop at the same time. Well, not exactly the same time, but shortly after. Roots build soil carbon and feed the soil biota. Once again, roots. Let's create root canopies. And we just don't want little, roots that are in the top, shallow roots, which flax would be considered that. We want things that are deeper. Corn roots, very deep. Milo roots, going deeper. Our wheat roots don't go very deep. I know everybody says, well, you can find roots very deep, but the majority of the roots in a wheat plant are in the top 8 inches, 6 to 8 inches. Whereas sunflowers and corn and milo will try and go a whole lot deeper. Even soybeans will try and go deeper. They just don't have a lot of roots. So they are, not a big root biomass sort of grower. Corn is perhaps one of the best for biomass. Oats are also outstanding for growing a lot of root biomass. So the foundation of soil health is really roots. Soil attached to the roots, the soil influenced by the roots. It's called the rhizosphere, and it's the most biologically active part of your soil. And you're going to see that every plant, some plants have much deeper roots, some plants have shallower roots. It's about making that canopy. Even if you only grow 2 plants together, or 3, ideally you'd grow 3. Pick one, a shallower, a deeper, and a deeper, or just go deep. But the idea is to really build that soil profile. That should be our goal. carbon from corn roots, and so you can see the difference between the roots and the stalks. We're always going to get a whole lot more, you know, from our root exudates and our roots. So one of the things that I really like about the German National Field Day, you can see the umbrellas up here, and everybody was in this trench looking at roots, is that they're behind every one of the crops, even the varieties. They'll have varieties planted in rows, and then they have this big trench behind, so you can actually look at the rooting. And you can see here, as we get into the subsoil, we're actually looking at the roots, again, leaving that oxidized carbon. And you can see how just trying to build up and streak this down. So the more organic matter we get, the darker our soils get. And here we go again. The darker our soils get. And the whole idea is to just keep that darkness going down, down, down. And now I'm really going backwards. All right. So this is, I wanted you to see a difference between here. So this is a solid yellow mustard cover. This is a multi-species cover. And you can see the differences in the soils. Plants really do control the amount of aggregation in the soil. They actually, some of them really make it tight. Corn will make it tight. Alfalfa will make it tight. Whereas legumes tend to loosen it up, make it a lot lighter. You can even smell that it's very different. In mustards, we're using a lot of mustards to control nematodes and whatnot. They don't do a bad job, but you can see that we actually get really nice crumb structure with the multi-species, where we've got a lot chunkier with the mustard. Plants work together. So again, the biology, the plant drives all that biology. The roots and the residues above ground drive the biology. Unite the physical properties of the soil with the chemical properties of the soil. And that's what creates soil health. But that also drives soil productivity, because if we have good soil structure, then we're going to have more roots. And if we have more roots, then we're going to take up more nutrients. That means that we're going to put more of our nutrients into our food. We're going to have nutrient dense food. We're going to put less of them into the environment. And we're going to actually, in the end, just really affect our health. And it's all driven by the rhizosphere effect, which is the next thing we're going to talk about, is how we can grow, increase the diversity in our cropping systems. So it's going to get a lot more practical. We're going to talk about intercropping, companion cropping, relay cropping a little bit. Yeah, all those really good things and what they do. But now we have the foundation, because we understand soil organic matter dynamics. So I'm still keeping on time here, but are there any questions? And please just turn on your mics and let's talk. Okay, is there anybody that's online right now that has a question? Well, we're waiting for the audience there. Okay, I got, no, nobody's got their hand up.
Anybody here have a question?
One moment.
Okay, one moment.
When you showed the field with the weed that did the white spots, how many years did it take to change that?
You know, that really, we did that in one season. When I showed you the next shot, that was one season. So we added about 70 pounds per acre of organic matter into the field. We experimented with 70, 40, 20 is what we did. And we found that actually, if we used 40 pounds of the pellets per acre, even on an annual basis, we started to really push the organic matter, and we really started to see a difference in the crop yields. And we were reclaiming eroded knolls very quickly, like in a year's time.
Good morning, Jill. Just a question here. Originally you have mentioned a change in soil texture from a clay to a clay loam.
Yep.
And to what depth was that change actually measured to? Just
Okay, that was,
interested.
yeah, that was David Brandt, and he was working with, I was about to say Ohio State, but it's the Ohio State University. They measured the change actually to 12 inches. So right next to him, his farm is the largest terracotta pot factory in the United States, using mining soil from their area. And his soils have now changed. They've given them, his farm actually stands out on the soil maps now because it has a different classification from the soils around him. But it took a lot of cover crops.
And now they attributed that change to the clay loam just on percentage organic matter?
Just in the change that was driven by the organic matter. So now that he's put so much organic matter into the soil, he actually has, instead of just a clay soil that has it has a fairly high CEC, but it holds everything tightly. Now his soils, they have a very different profile. They are what would be considered a clay loam.
Well, yeah, it's quite the difference, though.
Yeah, no, it's a monstrous difference. And honestly, at first, they didn't really believe it. And David had to go, he brought a lot of people out, and it wasn't until he brought Dr. Ratan Lal out to his farm that all that changed, because Dr. Lal is definitely considered one of the world's foremost experts on soil organic matter and carbon dynamics. And he came out and David said, I'm sure this has changed. And then they actually started to do the proper studies of it.
And you said that was Ohio State University?
Yes, Ohio State
Alrighty.
University.
Alrighty,
And-
thanks.
Yep, and you can look up, you can Google at any time Dr. Ratan Lal and find all his work. He's done some really, really great work.
Have you done any research projects with addition of biochar or worm cast?
I have not worked with biochar. I've only worked with compost.
Okay. Thanks.
Oh, you're welcome.
Doctor, I have a question for you.
Sure.
Here in Nebraska, or a lot of the corn belt, there's a lot of fungicide applied both to the seed and foliarly during the growing season, corn, soybeans, and wheat. What kinds of impact on the soil, if any, does that have?
Well, fungi, 90% of all fungi have nothing to do with diseases at all. Most of them are involved in decomposition, and really none of those woody residues break down in our soils without fungi. In fact, a tree won't break down in the forest. A dead tree won't break down without fungi, because it's the only thing that can actually eat the lignin and the cellulose fibers and break them down. And so when we apply a lot of fungicides, we are affecting our rates of decomposition at the same time, especially even though they're foliar. A lot of them are residual on the organic matter, so on the residues, in your stubble. And we do see that, a lot of people complain, well, I know in southern Kansas, they're like, well, are you going to burn that? No, I'm going to graze the milo stalks if I can. And that will help break it down. But a lot of people complain, well, things just don't break down. It's got to be the dryness and things like that. But no, some of it is just the fact that the fungi have been damaged by a lot of the things that we put on. And so they can't break it down. So things slow down. I mean, we see that. I mean, when we were using a lot of Ivomec in racehorses in Kentucky, a lot of the trainers were noticing that all of a sudden their manure piles just kept growing and they didn't break down at all. And part of that was because all the organisms, like the dung beetles and that were normally would be associated with that, with the manure piles, they were dying from the residual ivermectin. So, you know, there are unintended consequences of some of these things, but everything we put on the soil, everything we spray on our crops has a risk. I mean, it has a certain amount of risk, and it's about minimizing that risk to our soil environment. So one of the things I would say is that, you know, we really noticed with that sunflower crop, you can see that, you know, we were changing the disease profile too. And that really, I mean, having other plants in the canopy really does change things. Not having splash. That's the other thing, you know, I talked about that insulation on the soil surface. Not having splash is an amazing thing. We notice that when we're growing flowers, and squash, for example, if we can have a really good mulch on our, oh, that's me somewhere. Excuse me. If we have a really good mulch on the soil surface, then we don't get that soil splash, and then we just don't have, you know, rotting spots on our plants. We don't have the same problem with diseases on our plants either, because we're keeping that splash down. And so the soil doesn't get on the leaves, it doesn't get to travel up the plant. You know, and the other thing, it doesn't get airborne. I mean, a lot of these spores, I mean, we think about the time of Norman Borlaug, when we really had a really big problem with wheat rust. I mean, those spores were traveling for hundreds and thousands of miles. If we can keep things on the ground and we can keep them decomposing, we can actually reduce the amount of fungi that cause disease problems by just letting them rot in the soil, and letting the earthworms drag them in, and letting the microarthropods chew them up, because they actually prefer, most of those animals, the microarthropods, really prefer residues that are colonized by fungi, because they're more nutrient dense. So they're going to eat the fungi off first, which really is a good thing for us for disease for the next cycle.
Good morning, Doctor. Quick question. Weed and feed has become a really popular thing in the early season. So, like a 60-pound rate of nitrogen with herbicide, how does that affect the soil versus, you know, actually bedding or, you know, knifing different types of.
I love it. Weed and feed. It's the same thing that most people put on their lawns. Urbanites understand weed and feed perfectly. You know, the herbicides, a lot of our herbicides aren't nearly as damaging as they're made out to be, at least not from a soil health perspective. And I say that not because they're not damaging at all, because they are. It's about how we use them. So in people who have really active soils, generally speaking, we don't find traces of glyphosate. We don't find traces of the pesticides they've used over the season, because their microorganisms have broken them down and used them as a food source. The nitrogen, I understand why you do that, because, you know, it's about getting after the weeds. And the nitrogen will also carry up the herbicide, so we take things out a little better. I think, like anything, you know, I'm trying to push myself to reduce the amount of herbicides I'm using and the amount of pesticides just generally I'm using in my cropping system. So, you know, I've gone to an intercropping system, and I'm using companions. I use companions a lot because I find that in Washington, for example, we just have a really hard time getting a cover crop in the ground. We just don't have an extended season. You know, winter has been here for a month, and we aren't going to, you know, be able to we wouldn't have had anything that would have worked after a late harvest. And sometimes we don't get any moisture till we get the snow, which means that, you know, we're counting on things growing up the snow. So what I found is that companions for me work really well. I can increase my diversity. I can harvest my cash crop, and then I can have my diversity after. So that allows me to keep the ground covered a little bit and manage my weeds a whole lot better. And that's always my goal. I mean, I've got to manage my weeds better. There's some really cool stuff out there right now. I know, weed and feed's fairly easy, but there are also some beautiful mulching implements now. If you check out Dawn Equipment, they actually have some things that actually like will roll between the rows and things like that. I've used weed burners. I don't recommend them in the dry country. Like Southwest Kansas, there's no way I'd be using a weed burner. I mean, that's just, why don't I just burn down the countryside sort of thought. But I think that there are some other ways we can help mitigate the need for that. And if you just do it once, get a good kill on it. And then if we can manage things better as we go forward, it's all good. I mean, it's like anything. I hope that people can solve their problems early on, and then get the soil a chance to work on all those things so that by the end of the season, we aren't seeing anything. So, whereas I'd encourage you to stay on the course, but make sure that if you are going to use your herbicides in that way, make sure that you're getting the best bang for your buck. So, are your are you using the best adjuvants? Have you got the pH right? I know the fertilizer will help with that. But there is a lot of other additives you can use in there to make that super duper effective, so that you're only using a herbicide once as opposed to the rest of the time during the growing season. And then it also means that you can cut back. If you can make it more effective, then you can cut back on the actual amount of active ingredient. And there's a lot of research out there on those topics. So I'd encourage you to sort of look at some of them as well.